Hello, this is Patrick Fleming, and I will be presenting Lab 4 on oscillations today for Physics 1 at Georgia Tech. The objective of this lab is to analyze the motion of a mass attached to a spring that oscillates in the shape of an arc. We will use the momentum principle, which basically states how the net force will affect the object. We have already used this before and know how to apply it. But we will also use the energy principle, which is new for us. Basically stating that the total energy equals the kinetic energy plus the gravitational potential energy plus the spring potential energy for this particular system. The total energy should equal 0 if the energy principle is satisfied. So we will track our oscillating spring using tracker. This way we can record the motion of the object and create a computational model based off the object. So what we can first use this data for is finding the spring constant. And how we do this is by some formulas that we learn. T equals 2 pi over the frequency, and then that equals the spring constant, which we'll be looking for, over the mass. So after we combine the two formulas, we can find the spring constant, which we find to be 6.89 newtons. So we need to add code to our computational model to make it correct, and we need to state the energies that apply to our system. The kinetic energy being 1/2 mv squared, the potential gravitational energy being mass times gravity times the distance, and the spring potential energy being 1/2 the spring constant times s squared. So we will use this in our code to find a functional computational model. So first we have to use the mass given, input that into our code, and we also input our different vectors. So force of gravity is negative mg. The net force will be the force of the spring plus the gravitational force. The ball velocity equals the initial ball velocity plus F net over m times delta t. This is part of our Newton's second law momentum principle. Our ball position, we're just going to update the position in the while loop. Also, we need to find our L, so that's going to be the ball position minus the spring position. Need to find our L hat, and with using all of this updated code, we can run our computational model. The blue arrow is going to be the potential spring force, and the black arrow is going to be the gravitational force, potential gravitational force. And these are very helpful for showing us the potential energy while our system is in movement. So with our computational model accurately displaying what we saw in our video, we can see if the energy principle is satisfied. When we graph our energies, the yellow line is going to show the total energy, which is going to be 0, which means that the energy is conserved in the system and the energy principle is satisfied. So our next what does it mean question, basically asking the difference between the X oscillation time and the Y oscillation time and why there is a difference. Why we see a difference between the period it takes for the X to oscillate and the Y to oscillate for our mass spring is the way that it moves in our computational model. As we can see, it oscillates in a type of oval, which would make our X oscillation longer than our Y, which would be the reason that it has a longer time frame. So, thank you for watching today. I hope you learned some physics, and have a nice day.